So let's continue where we were last time. So we were discussing the main point of lecture 3 and problem set 3 is to calculate different kinds of probabilities, right? Different problems that just basically calculate probabilities. The number one thing, right, to remember when you calculate probability, right, and problem 3 here would be the sort of the main kind of like highlight is that when you calculate a probability, right, you need to decide the sample space first, okay, as reflected in, looking at the size of the sample space. And then from there, right, proceed to looking at the event. Again, right, I think that you guys have the habit of, or you just want to write down the answer, right, once and for all and be done with it and not even think about it twice. That's basically a bad habit, okay? It's possible with an easy problem. But when you start dealing with a more challenging problem, then if you just want to jump to the final answer, it's mostly impossible, right? And you have to kind of proceed step by step. And the first step, right, it's usually skipped over, which is very important, is to think, right, what perspective that can be looked at, right? The problem from which the problem can be looked at, and with the right perspective, the problem will be easy. With the wrong perspective, the problem will be impossible. And besides that remark, right? Also, of course, right, the other remark is that it doesn't matter what perspective you take, the final answer should always be the same, right? In terms of probability. So in that sense, like whether you choose to distinguish items in your count, or when you choose to introduce orders where appropriate, okay, or choose not to introduce orders, again, where appropriate. Sometimes like the choice of order is not up to you, but if the choice is up to you, those choices would not matter, okay, in the final probability calculation. And besides that, the rules of probability that we talked about, right, in lecture 1 applies. For example, inclusion-exclusion formula. If you don't apply the inclusion-exclusion formula correctly where it's required, right, your answer will be wrong. Besides that, right, it's just really a mix of combinatorics principle with, and to find the probability. Now, so we were, right, looking at this kind of important problem last time, which is the hat problem, right? Again, the context is, right, and people, right, throw their hats together and pick the hat out at random. And we want to look at, right, the probability that no one gets their right hat. And so from the context of counting, this is similar to the so-called rearrangement problem, where, right, basically you have, let's say, n items here, 4 items. You permute them, right, in a line, and you want to ask for the probabilities, right, that no items are in the right position, okay? So here is a case that no items, right, are in the right position, while this, right, is a case where number 3 is in its right position. So it's not one of these cases that we want. Okay, and so this is a problem that kind of demonstrates a lot of principles. In fact, like all the principles we've talked about in class so far, right, comes in this example, this problem, right? The first one is the Morgan's rule, right? The Morgan's law. Because if you let EI be the event that the ith person gets their own hat, then the event that no one gets their own hat will be the intersection of all EI's complement, okay? And then, right, you would use the Morgan's law to turn that into the complement of the union. And then, right, the external probability says that the probability of the complement, right, is 1 minus the probability, right, of the event itself. from which, right, you would apply the inclusion exclusion formula at this stage, right, giving us this, which is the general, right, inclusion exclusion formula, which starts from, right, adding all the first layer probability, subtract all the second layer, add all the third layers, and so on, right, until you reach the last layer. Where, right, notice that here you only, so order does not matter, right? You only do it once for each layer. Okay, and then, right, the whole point then is we just need to calculate, right, these probabilities and then plug it into the sum and sort of, right, get the answer from it. But there's kind of like a simplification step that we did not do, well, we did not get time to do, right? So basically, if you look at, right, the probability of, let's say, EI or EI-EJ, right, all of this can be done by counting, and that's actually, right, where combinatorics comes in. Well, we mentioned how with like a one person, right, with EI only, then you could, right, either use the counting argument, or, right, you can simply look at the ith person point of view and see that, you know, the ith person has n choices for their hat. Therefore, right, you know, probably simply is 1 over n, right? So that's sort of like the highlight about the points of view, right, that we talked about in the lecture. Okay, right here, right? So here, right, from this point of view, if you just want to look at the probability that the ith person gets his right hat, then this is a much easier approach. On the other hand, in the hat problem, right, this is not the end of the story, okay? This is really just a small part of the calculation. The calculation requires us to, right, calculate all EI-EJ, EI-EJ kind of thing. So that point of view, from the point of view of the ith person, cannot generalize, right, to the calculations for EI-EJ and EI-EJ and K and such. So for that reason, right, the counting argument, the combinatorics argument, becomes sort of like the same tool, right? The single tool that we can use to calculate all of these probabilities. And the principle, right, is basically, again, looking at the permutation, right, of n items. So that's why, right, it's over n factorial. And then, right, whatever you want to look at, EI-EJ, EI-EJ-K, that kind of thing, what it means is that, right, the items that you're looking at are in the right positions, right? So these are in the right positions. So they are fixed, right? And then, right, the rest can be permuted around, right? But of course, if you fixed, let's say, 3 items, then there's n minus 3 factorial ways, right, to permute the remaining items. So that explains, right, all these answers here. Okay. So this is why we stopped last time. Now the point is to plug this into the expressions here, right, and simplify for the final answer and see. Okay, any question before we continue with this step? All right. So I'm just gonna write this in with more space, right, so that we can see. So we have this 1 minus, right, and then the inclusion exclusion formula says it's a sum, right, of PEI minus sum over I less than j, EI-EJ, plus I less than j less than k, IJK, right, so on until -1 to n plus 1, E1, E2, yeah, where, right, PEI is n minus 1 factorial, PEI-EJ, minus 2 factorial Pijk n minus 3 factorial. Okay. All right. So now one thing, right, to note in this calculation is that all of these probabilities, right, are independent of I and j, right, or independent of the index. What that means, right, is when you plug this into the sum, right, they are the same for all. Basically, you sum over the same term. So basically, right, this becomes a product, okay, a product over, right, how many terms there are in the sum, right? For example, right, the sum, right, this is I from 1 to n, right, of PEI, right, is a sum I from 1 to n of, right, we can now plug this in as 1 over n, and that's going to be 1, right? So this right here is 1. Okay. And now we'll do the same thing, right, for this term right here, right? So this is sum over I less than j. Oh, by the way, right, the 1 is because, right, there are n terms times 1 over n, right? So that's 1, right? n terms times 1 over n, so that's 1. So now if we sum over this PEIEJ, right? So that will be however many terms there are, right, times the probability, which is n minus 2 factorial, or over n factorial. Okay, the question is, right, how many terms are there in this sum? What do you think? How many terms are there in this sum? Any suggestion?
-1.
No, right? So think about it. Let's say if you have n equals to 4, right? Then the sum over I less than j will include how many pairs? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Correct? So that's not n minus 1. Any other suggestion? Okay, look at this. From 4 numbers, right? How do we get these pairs? We pick 2 numbers, right, out of 4 numbers where order does not matter. So the total number of pairs, right, in this particular case should be 4 choose 2. What is 4 choose 2? 6, right? 6. So in general, what should the answer here be for the number of terms?
So n choose 2.
Correct, right? N choose 2. And what happens when we look at this? N choose 2 is n factorial over n minus 2 factorial times 2 factorial. And therefore, we have one cancellation, leaving us with 1 over 2 factorial. So therefore, right, the second term is 1 over 2 factorial. Okay. Any questions so far? All right, let's look at the third term. So again, right, this is the probability right? And how many terms do we have in that sum?
N choose 3.
Correct. So that will be n choose 3. So that will be n factorial, n minus 3 factorial, 3 factorial. And so, right, the cancellation will go like this, and we have 1 over 3 factorial. So can we see the general pattern? Right. For this particular problem, we have 1 minus 1 over 2 factorial plus 1 over 3 factorial. All right, so the next term would be minus 1 over 4 factorial, right, and so on. And the last term here will be what? What would this be?
1 over n factorial.
Correct. Right, so let's write that. So basically we have 1 minus 1 minus 1, 1 minus, right, 1 over 2 factorial plus 1 over 3 factorial, right, so on, right? And then minus 1 to the n plus 1. But of course, right, the cancellation here would go 1 over 2 factorial, right, so on. And the last term we minus 1 to the n. And this exactly is the probability that no one gets the right hat. All right, so it simplifies that expression, which is, again, right, compared to the original expression, right? The original expression, as you can see, right, is kind of complex, right? But it simplifies to only this. Okay. All right. Any question?
Can that be written like more simply?
No, that's as simple as it can get. No more.
Like the sum of negative 1 to the n over n factorial, it doesn't converge to any like particular number? Or I guess never mind. It's not like an infinite.
We, it is a, so yes, you'll get, I'm getting to that point, which is, right, what this sum would be if you take the limit. But notice, right, that this is a separate question, or the question that we asked, right? What is the limit as n goes to infinity of this sum? Right? A probability no one gets the right hand. But notice that that's not the same. That's not the same as saying what this is, right? This is just a particular sum, and taking a limit is a different question, right? I'm saying this because, as you see, right, this answer actually is a nice answer. But again, for some reason, well, in the previous time I taught this class, which in the spring, people would give me this answer right here, okay? and think that somehow that's the right answer. And again, right, without, you know, saying it however else, this is just nonsense, because this is just some sort of like extra information to see when n is pushed to infinity, right? The question by itself is not about that. It's just for n persons. Okay. So, but anyway, right? Yes, this sum right here actually has a nice limit. What would that limit be?
I think I've seen it before. It might have like Euler's constant, but I don't remember exactly like what the exact expression is.
Euler constant. I'm not sure what Euler constant is, but right, this actually, yeah, this is just connected to, right, the expression, let's say e to the x, right? What's e to x? 1 plus x squared over 2 factorial plus x cubed over 3 factorial, right? So on and so forth, right? This is the Taylor expansion, right, for e to the x. So if you look at e to the minus x, that's 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, right? Sorry, plus x over 4 factorial, right? And so on. So if you look at e to the minus 1, you get, or rather, right, sorry. So yeah, so you plug in 1 here, right, because e to minus x already, right? So if you plug in 1 here, you got 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial and so on, which is exactly this sum, right? And so this will converge to e to the minus 1 as n goes to infinity, which is connected to the Poisson distribution, which we'll discuss later in this class. All right, but again, right, I emphasize that this is a extra question that bears no connection, right, to this question overall. If you give the answer as 1 over e for this question for some reason, it's just totally wrong, okay? All right, any question about this? All right. So the last problem, this problem set will be this one. Okay. And we mentioned this one, right, before, as some sort of like, you know, counting problem, right, where complement thinking is important. But let's take a look here. All right. So the picture for this question, right, is something like this. Let's say you have couple A, couple B, right, couple C, and couple D, right? And they're arranged in a line, in a row, whatever, right? The question is what's the probability, right? So I almost put a C in here, right? That, let's say, no couple, right? No one is next to their partner. Okay. And so on, right? All right. Anyone wants to suggest a probability here? If your, favorite activity is to come up with an answer right away. Any proposed answer? All right, if there's no proposed answer, what do you think is the right approach for this problem? Or what should we do to start getting to the right answer for this problem?
Probably use the inclusion exclusion principle again.
Good, but how do we start doing that, right? Because the inclusion exclusion principle or formula, right, starts with events, right? So what events do we want to look at here? Which, right? I mean, if you want kind of like want to use the, or anyway, right? Basically, inclusion exclusion formula. It can be a count too. Depends how you want to look at it. But inclusion exclusion formula, as we kind of look at right in this class, is something like this, right? I don't know. Does depends on how I put it, right? So the point, I'm just writing down something here, but the point is, right, you want to basically define, right, these events. So what do we have in mind for these events? Or we need to spell out, right, what events we want to look at and how many of them. Right, so that's the challenge of these kind of problems, right? You just don't come in right away and say inclusion, exclusion. You have to name the event correctly, to name the probability you want to calculate correctly, and then see how that leads to the inclusion, exclusion formula. So what events do we have in mind here?
I guess the events would just be every possible ordering between these eight people that there is.
That's not an event, right? Every possible ordering is a count, right? So if that's what you're referring to, you're referring to the sample size. If according to language, you say, right, if you talk about all possible ordering, then there's a factorial ways, right, to arrange eight people on the line, right? But that's not an event. Event is, again, right, something happening, right? Like the I person getting the right hat is an event. The I person and the J person getting the right hat is an event, right? So the event here is similar to the hat problem, where you let EI be the event that couple I stay with each other. All right. And so then in the language of the problem, what probability are we looking at? If we let EI, right, be the event that couple I stays with each other, then in the language of the problem, what probability are we looking at?
Well, one minus the probability of like EA and AB, I mean, and EB and so on.
Uh, let's explore that. 1 minus P of E1, E2, E3, 4. So what you're saying is the question, is what the question is asking? Is that what you're saying?
Yeah.
All right, let's see. Okay. That's a good suggestion, but let's see. Let's translate this, right? Well, 1 minus this will be the probability of its complement. Agree? That's just by definition. Now, what is the complement of the intersection? It's going to be the union, right, of the complement. That's De Morgan's law. Okay, now read this out loud in English. What does that mean? I mean, not the probability, just the event. What is E1 complement, union E2 complement, that kind of thing? What is that in English?
Couple A doesn't stay together or couple B doesn't stay together and so on.
Correct. Is that equivalent to no one next to their partner?
No, because that's just or.
Good. Excellent. Right. Excellent. So what do we want here? If we want no one next to their partner, what should we have here?
So we need ands for the complements.
Correct.
Okay.
Correct. So we want and here, right? Which means now you can fix this. If we want and here, then we want or here. Correct. Or we would want or here. Which, by the way, right, is a very similar structure to the hat problem. So, right, we want 1 minus P of E1, union E2, union E3, union E4. Okay. Which, of course, right, means that we just have to calculate this and then we do 1 minus it. So, right, so we will apply the inclusion exclusion formula for this one. Any questions so far? All right. So now, right, it'll be 1 minus, again, right, let's say sum, right, PEI 1 to 4 plus sum of PEIEJ. Right, I less than J minus P of EIJK. I less than J less than K. And then, right, because this is only 4 events, so we can do the last one like this. Okay. So that's that. That's inclusion exclusion at the 4 set level. All right. So now again, right, all we have to do now is to calculate each of this, plug in the sum, right, and then see if, you know, well, basically, roughly, right, finish the problem. So what is PEI here in this case?
It's the probability that couple I stays together.
Sure. What is the answer now, right? We want a number. What would that be? So we have to do counting, right? Where here the sample size is a factorial. So the denominator is over a factorial. The question is, what is the numerator?
Is
How
it
many ways? Yeah, go ahead.
um is it 2 times 8 maybe?
No.
Okay.
If you arrange right four couples, we talked about this question before. If you arrange four couples right in a line, how many ways is it for couple, let's say couple A, to stay next to each other? How many ways for the couple A to stay next to each other? Well, couple A have to stay next to each other, right? So that they count as a unit. How many are left? Six more, right? So plus six. So in total, there's seven, right? There's seven units that move around. So that's 7 factorial. There's a two because, couple A can switch among themselves. So it's 2 times 7 factorial. All right. So that's PEI. How about PEI EJ?
Six factorial times 2 to the 2, and then over 8 factorial.
Correct. I think so, right? Yep. 6 factorial, 2 squared over 8 factorial. All right. So we got the idea, right? EI, EJ, EK will be, is it 6 factorial or not? Yeah, two units and four left. Yeah. All right. So EI, EJ, EK will be 5 factorial, right? And EI, E1, E2, E3, E4 will be 4 factorial, right? 2 to the fourth over 8 factorial. Okay. Any question about this? So now, right, you just plug these numbers in, right, do the sum. And unlike the hat problem, right, if once you throw in the number of terms, um, there's not much simplification going on, right? So we'll just leave the sum like that. Okay, any question? All right, so that finished lecture 3, right? Which basically introduced you to probability calculation, right? Using combinatorics, but also, of course, employing all other probability principles, right? That we've done before. In particular, right? The inclusion exclusion formula, the Logan's law, right? And calculating probability by the complements. Okay. So now, give me a moment and let me transfer the next lecture into my iPad. So, oh, wait, hold on. Should do this. Okay. So now we finished, I guess, with probability, or at least we're more or less done with, right, basic probability calculation. Now we move on to the next topic, right, which is actually very important in probability itself, but also, of course, right, much more important for more advanced topics using probability like stochastic processes, statistics, right, especially Bayesian statistics. And so basically, what's the idea, right, of conditional probability? So suppose you have two events, right, E and F, and the requirement, right, is that the second event, the event that you will condition on, has positive probability, all right? Then the conditional probability of E given F, this is like the name, right? This is the terminology. We'll refer to this as probability of E given F, right? It's defined like this, okay? So this is just a definition. We'll talk about the meaning of this definition later on. But, right, notice that we require this to be positive because we divide by it, right? Otherwise, the definition won't
Wait,
make sense.
Professor.
Yeah.
I don't see any change in the screen. We're still looking at problem 7, at least for my screen.
Oh, no, I really appreciate it. I think there was a freezing in the slide. It happens when I switch things, so please let me know if that happens. Sorry about that. All right, so lecture 4. Okay, thank you for letting me know. Okay, so good now. Let's start again, right? Thank you for letting me know. All right, so yeah, so yep. Okay, again, right, new lecture. Conditional probability. Right, so when we have two events, okay, such that, you know, the one that we want to condition on has to have positive probability, then the definition is the conditional probability of E given F will be denoted, right? E vertical line F will be defined like this, all right? Which is basically, right, the joint, or, you know, and, right, over the marginal. This is the language of random variable, but you know, you'll see later, right? The joint over the marginal is a conditional. Okay. But yeah, right, the technicality is that, right, whatever you condition on must have positive probability, right? Otherwise, you know, the definition won't make sense. Okay. Any questions so far? Again, right, this topic is super important in like more advanced topics using probability like stochastic process, Bayesian statistics, and things like that. Okay. So, right, it's actually very important for us to understand the meaning, right, of conditional expectation, conditional probability, right? And so here, basically, when you condition on something, that reflects the knowledge that you know that it has happened, right? The event that you condition on. So you have knowledge of F. Okay. Meaning that, in a way, right, you can think of F as your history has happened. Okay. And then based on that, right, based on this knowledge, you want to evaluate the likelihood of E happening. So this is what you don't know, right? This is what you don't know. But F is what you know, right? Okay. And the key idea, right, and this is why conditional probability is, or conditioning in general, right, is a very, very important tool for more advanced topics, is because, right, information changes the likelihood calculation. Okay. So what we've been doing so far, right, when we look at probability of an event, you can also think of it as calculating with no information, right? No extra information. All right. Everything being equally likely or something like that. So, but with an extra information, right, the probability will change. Okay. So I think I kind of gave away the example there, but let's take a look, right? Suppose we roll a dice, right? Then the probability, right, of rolling a 2, right, will be 1/6, right? But if I know that I roll a even number, right, then how would this change the probability? Or would it change the probability? The answer is yes, it should, right? In fact, right, intuitively, you should see that the probability now should become higher, correct? Because now, right, you want to find the likelihood of landing on a 2 among the even numbers rather than, right, among the 1 to 6. Okay? So let's see, right? According to the definition, if you let E be the event that you roll an even number, roll a 2, right? F as the event that you roll an even number, right? Meaning that F is the event 2, 4, and 6. Then probability of E given F here, right, is PEF over PF, right? Which will be, right, well, of course, if you intersect a 2, right, with 2, 4, 6, then you just get a 2, right? Or rolling an even and rolling a 2 is just rolling a 2. And then, right, P of rolling an even, right? And rolling a 2 is 1/6, rolling an even is 1/2, giving us a probability of 1/3. Okay, so far? So the point, right, is that the knowledge, right, of the roll being even will change, right, the calculation of the probability, right? It will move the 1/6 to 1/3. Okay. All right. So, all right, that's what is the thing here, right? So I mentioned that before, right? These are a few examples where conditioning is very important. Now, it's very important. So let's try to, right, talk more in depth about this idea. That, you know, basically, right, it's very easy for a student to confuse these two things, right? Meaning that they could be thinking of P of EF, or they could be talking about P of even E given F when they think of PEF, and vice versa. All right. And so it's very important to distinguish these two ideas. And yeah. So, right, the key difference is in what kind of information, right, is available. In P of E given F, right, you have the knowledge that F has happened. But in this, right, which is basically the joint probability here, you do not have any information about E or F happening. Right? So here you ask for PEF together, while right here, you know F has happened and you just ask for PE. So that's the meaning, right, of these two probabilities. Okay, so they're different in meaning like that, in terms of the information available. Okay, but now let's look at, right, further property. This expression, right, the conditioning is not symmetric. Conditioning is not symmetric, all right? Meaning that E given F and F given E are two different things. All right, let's demonstrate this. Again, right, let's look at the example where we let E, right, be the event that we roll a 2, and F is the event that we roll an even, right? So we talked about how P of, right, E given F is 1/3, right? Now, what is P of F given E? What do you think?
1.
Correct, right? Exactly, right? Because if you know that the row is a 2, then it must be an even number, right? And finally, what's P of EF?
Just 1/6.
Correct, right? So demonstrating that all these three are different, right? PEF is just rolling a 2 and an even number, which basically doesn't do anything, right? Because a 2 implies an even number. But condition on an even number actually changes this, right? So correct, right? And of course, right, EF and FE are the same thing, right? But E given F and F given E are not the same, okay? And so, yeah, we talked about that, right? And right, it's very important to recognize that with the problems we'll be doing, right, or with what you'll be seeing, um, you know, in real world example and things like that, people don't have right to ask you, tell me the conditional probability of E given F, that kind of thing. They could, but let's face it, right? Not many people, let's say, are aware of probabilistic language, or care to use right the precise language when they ask a question. They tend to talk about things in English, right? So in English, the signal, right, that conditional probability or conditioning is in the air is when you hear the word if. Okay, if will signal that, again, of course, it's not 100%, or I cannot guarantee that this has happened, or this is the case, but right, usually when you hear the word if, right, in the probabilistic context, that should be where conditioning. Why? Because the word if, right, kind of gives you information, right? If, right, if the row is even, right, if row is even, right, find the probability that row is a 2. Right, notice in this question like this, right, it did not even reference the word conditional anywhere in this writing. However, right, your task when you read this question is to translate it into PE given F, because the word if is given here, right? Does it make sense? So you have to, right, be aware of the language, that basically when you see the word if, then even the word here is probability, that's a conditional probability. Is that okay? Oh, sorry, right? We're past the quiz time, so let me give you the quiz and then we'll continue. Um, you know what? Let's just give you this problem number 6 right here. Okay, this is the quiz for both part A and B, right? All right. So let's continue at 7:05. Okay, let's continue. Is there any question before we continue? All right. So, right, as we mentioned, I guess, right, the language for conditioning is if, while the language of, right, the joint is and, right? We talked about this before. All right. So we'll next discuss a very important idea called conditional thinking. Okay. And this actually gives the intuition to the conditional calculation. All right. So basically, when you condition on F, right, and whatever you put in here, because really, right, when you condition, F is a fixed event, right, and you just calculate everything based on F, then you could look at F as your new universe or the new sample space. Meaning everything, right, is viewed relative to F. Okay. So how would this be different? So for example, right, if you calculate PE given F, right, in the one that we talked about before, then if you do it by definition, you get 1/3. Now, this actually is done, right, over the original sample space, right, where you have 1 to 6 as the dice throw. But if you do conditional thinking, then you can move to the new sample space where 2, 4, and 6, right, are the possibilities because now you condition on getting an even thrown. So, right, if you're in this, then the chance of getting a 2 is 1/3. Of course, right, you have to recognize that once you condition this, events are still equally likely, right? And that's sort of like the tricky thing about conditional thinking. That conditional thinking is sort of like advanced, but easy for error, okay? So it should be used as an intuition tool, but calculation as done in this course will be required. Homework, exam, that kind of thing, right? To be done by definition, okay? So we do talk about conditional thinking as a tool because it's a very important tool to explain the idea. But at this level, right, because it's prone for error, we require that you give the answer by definition, right? In other words, if you use the answer, you give the answer by conditional thinking, you won't get credit, okay, for that answer on homework or exam. Even though the answer might lead to the same valid, the approach might lead to the same valid answer. That would not be the approach that we allow for, accept for, in terms of the formal answer for the exam and homework. Is that okay? All right. So, right, that's what I'm saying. It can give you a more direct way to get to the answer, but has to be used with care. So we're not gonna allow that for formal answers, but we're gonna use that for intuition building. Okay. Now, any question about this? Now, to show you, right, that conditional thinking actually is not a walk in the park. It's not easy at all. Let's compare these two examples, right? And what I'm asking you to do now is to read these two carefully and think, first of all, what the answers are for these questions. And are they the same answers? Are they the same probability? Okay. So I ask you to read these two questions carefully, come up with the answers for both of these questions, and right? Do you think they are the same answers, or do you expect them to be the same answers? All right, any input, any suggestion?
Um, I kind of wrote down like what the original sample space would be before we know that one of the children is a girl, and I just kind of labeled it like B and G. So you could do like BB, BG, GB, and then GG.
Right, that's the original sample space. You're correct. BB, BG, GB, GG. Okay, that's S. Okay.
Okay. And then F would be just BG, GB, and GG. So just one of them being a girl.
All right, that's not bad.
Okay. And then E would just be GG, and then it's easy, I think, to find the probabilities from there.
Which you suggest will be what?
Well, I didn't actually do it. So, well, probability of E and F would just be 1/3.
No, E given F then, right? Not E and F.
Oh, wait. Wait, no, yeah. Well, I was just doing like the top part of the expression. So yeah, E given F is going to be equal to on the top P of E and F, which would be 1/3.
That's wrong. So because PEF, if you want to look at it, right, it's really just PE, isn't it? Because E intersect F.
Yeah. Okay. Well, relative to yeah, right. Okay. Yeah, so that's
That's 1/4.
or I mean 1/4, 1/4, yeah. Okay.
So if you, so what you're doing is you want to do it by definition. P of E given F is P of EF over P of F, right? Which is 1/4, and P of F is 3/4, right? Which gives you 1/3, right? So what I was getting at actually was that since you saw that F is this and E is here, you could use conditional thinking to get to the answer as 1/3 right away. That's conditional thinking based on this, right? Again, you're doing what I would say you should do for the exam and stuff like that. That's correct. But here in this slide, we kind of like are aiming at conditional thinking. So, you could do that 1/3 as well. Is that okay?
Yeah.
But that's not the crux of the question even yet. There are two problems here. So are you saying for you in particular that the two problems have the same answer, which is 1/3? Or for anyone actually, right? So both of these problems, are they 1/3?
Oh, I just did the first bullet point. So I don't
Okay. All right, sure. I'll wait for the second one to see if there's any.
wait, he brings a girl and that's one of his children. So yeah, it must be the same answer.
Hmm. Right. So you think it's the same answer? 1/3, right?
Yeah, yeah.
Final answer.
Okay, well that means that it's probably not the right answer.
The answer for a second one is 1/2, not 1/3.
Oh, because now we in the first bullet point it could have been either of them, but right here it's just like we know that this one is the girl. Okay, I guess I see the logic.
Well, yeah, it's a bit subtle, more subtle than that, right? So here, the difference between these two, right, is that in a second, right, when your friend brings along a girl, what that means is now you can reference to the other child.
Yeah, so F
All
would
right.
just be like BG and GG if we just say that the second one is
No, incorrect. F is not BG and GG. The reason is you don't know if this is an older daughter or younger daughter, right? So we're not, your friend never tells you this is an older daughter. When you say F is BG and GG, you're kind of saying that, right? This is an older daughter or something like that, younger daughter, right? That's not that even. When your friend shows you this girl, then F is the event about the other child, which is just B and G. That's it.
okay.
That's the subtlety here, right? When he brings along a girl, then you can think of the other child who's not there at the restaurant. Clearly, right? That child can only be a boy or girl. Therefore, probability that he has two daughters is the same as probability of that child being a girl, which is 1/2. Does that make sense? While in the first example, this is F, which you correctly pointed out because you don't have any other child to point to.
I
All
mean,
right, go ahead.
it makes sense, but I feel like if I also just kind of assigned this girl that we see that the friend brings along, if we just assigned her an actual position in that ordering and we just make F, B, G, and G, G, we would get the same answer because E is just one,
Well,
two.
but when you do that, you are using extra information that you don't have, right? Because on what basis can you assign her a position? Your friend never tells you anything, right? At least the question didn't give you that information. Is that okay? Because if you use that extra information, you may basically change the problem, right? And the whole point, or I guess the whole difficulty of the question is he never tells you any extra information about this girl, besides the fact that that's his daughter. That's it. Does that make sense?
Oh, I'm not fully understanding why the order of the ages of the daughters matters for the first bullet point.
The age matter? Not
Or the
well.
ordering
It's
at
not.
all.
Well, that's because when you have two children, right, the order matters to begin with, right? Order naturally matters when you look at a sample of, two coin toss, right? Head, tail, and tail head, because you want to look at equally likely, right? This is exactly one of those things where I say you have to build order into your count here. Exactly the same concept, right? Order
Okay.
must matters. Yep. Right. So exactly, right? When you contemplate these two problems, there will be a lot about the foundation of sample space, probability, and that kind of thing that comes to mind in exactly the whole sample space. The questions that you've been asking, both of you, right, exactly center around that. And that exactly is why I keep harping on, right? Getting the right sample space is crucial, right? Because exactly, I mean, it's okay to be confused about these things. They're not easy, but right, that only demonstrates that if you don't get the sample space correctly, right, then your probability calculation will not be correct. Okay, and again, these two are very subtle questions. Okay, guarantee you, like if you ask people on the street or people who have taken probability, most of them will get it wrong. They either will think that they're the same questions, meaning right the same probability, or they get a probability wrong, whatever, right? But I'm putting these questions here, right, not to kind of say that you have to get this right away or they're easy, but exactly in a contrast, I want to put this here to show you that conditional thinking, right, while a powerful tool, is tricky business because you have to use just the right amount of information, okay, that you know, not more, not less. And sometimes the information of having a girl bringing along or being told that one of the children is a girl makes a big difference, right? It's not the same kind of information.
So for the second one, can you just say that the probability of the other child being a girl is 1/2? Like, is that the reasoning or is that wrong? Can you re-explain that part for the second
Yeah,
bullet
no.
point?
I for the second one, yeah, that's exactly it, right? Because you have the other child, you only have a girl, right? So the other child who's not here in the restaurant, the probability of that child being a girl is 1/2. Therefore, right, 1/2 being two daughters. Correct. That's it. That's conditional thinking. Given that you already see a girl, a daughter, you can top with the other child, right? You move to a new sample space. All right. Any other question? Okay. We'll address this a bit later. But here, right? Here is basically a device to recast the example I just showed you, right? So that it's convincing to you that the answers we give is correct. And again, right, this is just basically multiple ways to cast the same problem, right? And the more stories, the more ways you can see the same problem, the more you can be convinced that your argument is correct. How so, right? Basically, right, the boy girl story, even though, of course, right, this is could be an interview question, even, right? The reason, of course, is that it sounds like a conversational story, and it makes it more confusing, right? It's restaurant and bar and stuff like that. But you take away all the bells and whistles, right? It's about tossing two fair coins. Okay. But what's the difference between these two cases? I guess I just show you, right? But if you didn't see it, right, can you think about if your friend, right, toss two fair coins, right, in these two bullet points, right? What's the difference between the two in terms of the information he tells you or he gives you? Right, you have a friend, right, who tossed two fair coins, and let's say you're looking for the probability of having two hands, right? But
I mean,
what
I
would
guess the difference is that the information given is ambiguous as to which coin it applies to.
right? No, but I guess if you didn't see the bullet point in the next slide, right, then that's fine. But if you saw it, then right, that's what I wanted to show you. Basically, the first one, right, is your friend didn't show you anything, right? He just verbally tells you that one of the coin after he tossed them is a head, correct? But the second one, he takes out one coin and show the head coin to you. You understand? And that's the difference between these two cases. All right. And that, of course, right, you see that. But
Could your reasoning for the second one also just be that like instead of age, it's an order? So like for the second one, it eliminates the guy bringing the girl, eliminates boy, boy, and boy, girl. Like if you
Incorrect.
think of
Again, right? I know that it's very, very itchy to get to drag the age thing into here. But if you eliminate boy, girl, whatever, you're trying to say that the daughter he brings into the restaurant is an older daughter, right? Now, that information is not in the problem, right? That information is not in the problem. In
I
fact, right,
see.
notice I highlight this word here. In the second experiment, right, your friend has to randomly pick a coin to show you, and then you see that it's a head. All right. It's not like he picked the first coin to show you. I guess that's the same thing too. Well, you can think about it. But here, right, in this, you can also have the third bullet point here where your friend tossed two coins and he picks the first coin to show you. That's what you guys are thinking of. All right. That's what you guys like to think of. But here, right, he can also randomly pick a coin to show you. And the one he showed you is a head. Is that okay? That's actually the second bullet point. So there's no order in terms of how the girl comes in, older or younger. Well, that still come out to be one half. All right. Any other question? Okay. So now let's take a look at the third one. Okay. So this is actually, right, referred to as the E before F kind of probability. All right. So here's a interpretation that actually has a gambling flavor to it. I think it's called a game of crap, CRAP maybe, I don't know. But basically you toss two dice, all right, until you see a 7 or 11. All right. I think maybe there's some other variations of the sum, but basically I think you want to get a 7 or 11, right? That's actually, by the way, the 7-Eleven, convenience store comes in, I think. But anyway, right? Now you want to suppose that's your game anyway, right? You want to find the probability that you'll see a 7 before an 11. All right? That's sort of like the context here. Now, first of all, right? Given the way the question is phrased, again, I'm just talking about natural feeling here, right? That sounds like a complicated question, isn't it? Because you have to look at the first throw, the second throw, the third throw, right? Things like that, isn't it? And then see if it's a 7 or 11, that kind of thing. So we're looking at infinite sample space here, right? And then in that infinite sample space, we have to look at sequence where 7 comes before 11 or E comes before F. But is there a way for us to solve this quickly, easily, without going to an infinite sample space? Again, right, this is showcasing the power of conditional thinking. Any suggestion? Here's the thing, okay? You want to keep doing it until E or F occurs, right? Or C, 7 or 11. The language there actually it implicitly says that you are conditional E given F. Oh, sorry, E union F. That will be your sample space. Why? Because you keep doing it until E or F occurs, correct? So you are conditional E union F. That's the key to cut through the infinite sample space thinking. All right. And right, once you recognize that, then what are you asking for? Asking for E given E union F. Right? Because once you see E or F, once you're in that sample space, what's the probability that you see E instead of F? Right? That's E before F. Does that make sense? And once, right, you recognize it like that, then the answer is easy because it's E intersect E union F over P of E union F. So the final answer is just PE over P of E union F. That's it. That's the answer for, that's the same as P of E before F. Now, of course, right, if they are mutually exclusive, you can write this as PE plus PF. But, you know, like this, right? 7 or 11 are mutually exclusive, so you can add the probabilities. But I just want to leave it like this in case, right, E and F have something in common, right? They have non-trivial intersection. But the point, right, is that a question like this, right, which pose a question as an infinite sample space or, you know, has a flavor of stochastic process because you keep doing until something happens, can be solved, right, using conditional thinking. Again, right, not trivial, not easy, but just showcasing, right, conditional thinking approach. Any question? Well, well, I guess while we're on this topic, right, let's talk about the Monty Hall problem. You know what? Let's go back to this. Let's do a few problems before we look at this. Okay, let's maybe, right, do this first question. We'll do one or two questions, and then we'll come back to the Monty Hall as the kind of cap of today's lecture. So again, right, there's nothing fancy about this kind of questions. Just define the events and use definition, okay? All right, any suggestion or input about the answer here?
Is it 10 over
Go ahead.
36?
10 over 36 is the answer you suggest?
Yeah.
Okay, can you explain?
I think the sample space is just 36, but the event is so one is 6 and the other is 1 to 5, and this happens like times 2, I think.
Yeah, you are kind of using a, let's see, okay? So what you're saying has a lot of chance for error. I'm just saying that, all right? So let us phrase it carefully. So E, right, is the event that we land on at least 1, 6, right? And F is the dice land on different numbers. Agree? So we're gonna, the problem asks for P of E given F. Right? Agree? So definition, right? So far, nothing I've written down can be wrong because I'm just following, right, procedure. All right, now let's tackle PF, right? What's PF? PF would be
Would it be 30?
30 over 36, right? We're not asking for the count, right?
Oh,
So
right.
30 over 36. Okay, good. Now what's PE? PEF.
Is it 11 over 36?
Okay, is that true? So one of them is a 6, right? So 1, 6 and 6, 1, that kind of thing, right? 12, but subtract 1 because they don't land on different numbers, so that's correct. All right, so the final answer will be 11 over 30, right? Agree? So yeah, right. Oh, sorry. Hold on. Why is it 10? Is it 11 or 10? At least 1, 6 and land on different numbers. 1, 6, 6, 1. Why did I write 10 here? Did I make a mistake in this answer? One, 6, right? 2, 6, etc. Right? Up to 5, 6. Oh, yeah. No, it's 10, right? And then if you look at this, it's 6, 1, 6, 2, up to 6, 5. Right. So yeah, it's not 6 plus 6 minus 1, right? Because the 6 count both here. So it's 10. Is that okay? This is 10. All right. But anyway, right? So the point is you must do all these things in a conditional probability calculation, right? To make sure that your calculation is correct. Otherwise, right? I mean, again, I guess an error of 11 or 10 here is kind of tolerable in the sense that, yeah, it's a miscount, right? It's a miscount. But something like this, if it's wrong, it won't get credit on the exam because, right, it has no work, things like that. All right. So this is the format that you should follow. Right? Just even like for partial credit and things like that. Okay. Any question? Okay.
Really, yeah, I have a question.
Go for it.
So it just occurred to me that probability is going to be proportional to like the number, like in this case, you can see that it's just like a number over 36 for each cases. So can we kind of rewrite this expression as just like the number of E and F over the number of F in terms of like the number of times it occurs in the sample space, and it's kind of the same expression?
So again, that sure, in the sense that, right, you just basically want to cut through the count over 36, right, and look at just this count. That's okay-ish, right? But I would discourage that because first of all, right, having the denominator of the total sample space doesn't cost you that much to begin with. And also when you try to keep those counts in your mind and you don't write down the probabilities, again, I'm just predicting that numbers might be shuffled around, maybe an error got made somewhere. And also it can drag you into conditional thinking, right, incorrectly. It's just all those things, right? I mean, what you say is true in principle, is correct in principle. In practice, I would say that, right? And again, right, the thing is just basically PEF, right, or PF. Yes, what you're referring to is the 36 will wash out. That's correct. But like I said, right, when you calculate the probabilities, I think the brain works better if you separate these two calculations out. Does that make sense? I would suggest that rather than skip through the one step. It's probably not too much gain and more chance for error. All right. Okay. All right, let's look at this one as the last question, and then we'll go back to the Monty Hall problem. All right, so how will you approach this problem? One second here, right? I'm trying to see, hold on. Oh, sorry. This one has a point to be in this kind of question, but it's not really, well, there's a conditional stuff going on here, but it's not directly a conditional question. There's a point for it to be in this part. Let me just skip over this and let's see here. Yeah, let's look at this. All right, so there's a point for the previous one, but it's not directly a conditional question. It demonstrates another point in the lecture that we didn't get to yet. So let's look at this. Oh, by the way, right? So there are actually two questions here, right? With replacement, without replacement. So let us do the with replacement case only. We'll leave the rest, right, for next time. Okay. So basically, right, the urn has 8 white and 4 whatever, right? Let's say 4 blues, whatever, 4 black, right, whatever. Okay. And then you draw 4 balls from this urn without replacement, with replacement, sorry. Okay. Then what's the conditional probability that the first and third balls drawn will be white, given that you have exactly 3 white balls in the sample? Okay, so E is what? First and third are white, right? F is sample has exactly 3 whites, right? And so P of E given F is PEF over PF, right? Now, what do we want to note about this question? What sample space are we working in? And here, right, is exactly a case where you do not want to wash through that sample space, right? Spelling this out will be important. What sample space are we working in? What's the sample size? If you draw 4 ball with replacement, right, what's the sample size? So what's the size of sample space? Twelve to a 4, right? But the thing to note here is that because you refer to language of first and third ball draw, here order must matters in the way you count, because you distinguish first, second, third, and fourth ball. All right. So when you do 12 to a 4th, your order is built into, right, a sample. But basically, you have to pay attention to that, especially when you do it without replacement, right? If you do 12 choose 4, that may not be correct because you need to have the count, right, of the order, right, among the balls. Okay. So let's look at PF. What should PF be in this case? So PF, right, is divided by 12 to a 4th, right? But what's the numerator?
Uh, 8 to the third times 4.
That's missing one thing.
Oh,
8 to the third times 4 is
the
good.
order matters. Wait, does the order matter here?
The order does matter because we refer to the first and the third ball.
So then it would be 4 choose 1.
Yeah, or 4 choose 3, right? Doesn't matter. Yep, correct. Good, exactly. Again, right? So that's why you have to be very conscious of that. Any question about this? All right. What about PEF? So again, right, LB divided by 12 to the 4th. What's the numerator?
So you would have two cases. The first, second, and third are white, and the second case is the first, third, and fourth are white. So for each
So you're
case, it's
referring to you're referring to 2 choose 1 then, right? Out of
and
the, because out of 2 whites, right? Already, you just out of 2 spots, you choose 1 spot for the whites, okay? And
and and then you have the 8 to the third times 4.
correct. Correct. Okay. Any question about this? All right, and so, right, normally this is all you need because, right, anyone knows how to plug in, right? Like I said, do not get obsessed about simplification in this class. Don't care, don't need, right? So that's another reason why, let's say, for example, right, this is good enough. I don't need that, all right? But again, so that's for exam purposes and things like that. But here, right, let us kind of look at the simplification here, right? Because it's very tempting. what do you think PEF over PF is in this case? Again, right, it's not needed, but let's look at it, right? What's the number? Looks like 1/2, right? Okay. But so again, this step is not necessary at all. And you should not try this on the exam. But let's try to, but this is for educational purposes. What do you think, right, is the reason for the 1/2 here? Meaning, is there a conditional thinking that will back up that, yes, this 1/2 makes sense? Is there an intuitive way for us to say that, yes, this number makes sense? And by the way, I emphasize, this is the way you calculate it, okay? No deviation from this. We're just explaining a different way to look at things to enrich this experience. All right, so here's the conditional thinking, right? So here's a picture, right? This is first white, third white, right? And you want what? You want either one of this being a white, right? That's what you want. Oh, sorry. Sorry, you want, the sample has 3 whites to begin with, sorry. The sample has 3 whites to begin with, right? So basically, the sample has 3 whites to begin with, right? So if you just look at 3 whites, right, what possibilities are there? 1, 2, 3, 1, 2, 4, right? 2, 3, 4, right? Basically, and what else? 1, 2, 4, right? So these are the positions where the 3 whites can happen. Agree? And all of these are equally likely because, you know, you don't see any favor, right, around these positions. So this is like your F, your new sample space. These are the positions of the 3 whites. All right, now what do you want? You want the first and the third being white. Well, which ones are they? Well, they are this. Oh, did I miss something? So hold on. Oh, I list this twice, right? This is not 1, 2, 4. This should be 1, 3, 4, right? And this. So right out of this, there are 2 possibilities. So exactly, it's 2 over 4. So this is conditional thinking, right? This conditional thinking requires you to recognize that these 4 positions where the 3 whites happen are equally likely. All right, and that's why it's 2 over 4. But like I said, right, this is just illuminating this answer, right? The orthodox way that must be followed in this class is this way. All right, any question? Okay, so I think we'll continue with the multi-hall, right, example next time. Friday, right, is 4th of July, so we won't have class. All right, so we'll see you on next Monday.